Hello, everybody. So today we're getting into the second half of our Unit 2. We're talking about these systems. They're either going to be systems of equations or our systems of inequalities. Let's start off pretty slow by working with our systems of equations. Two learning objectives today. We're talking systems. So first objective, I can understand that the solutions of these systems are where the values are true for both equations or where the two lines intersect. I could also correctly define the type of system given its solutions. Little vocab for you. System of linear equations. They're just a grouping of two or more linear equations. The solution of this system in two variables is any ordered pair, any x comma y, that solves both of the linear equations. Here's the first example. Determine whether this given point is a solution. You have the point -3, 1. There's your x, y. Here's your system. Notice it's two equations. You have x minus y equals -4, and you have 2x plus 10y equals +4. There's our system. It's two equations. We have our point -3, 1. All we're going to do is plug in those values. Plug in x for x, plug in y for y. So I have -3, 1. I plug in my -3 for the x. I plug in my 1 for the y. -3 minus 1 is -4. That's true. Second equation, I'll plug in x in for x, y in for y. So I have -3 plugged in for x, +1 plugged in for y. 2 times -3 is -6. 10 times 1 is 10. -6 plus 10 is +4, which the equation said, so it's true. Since this x comma y makes both equations true, we know it's a solution. That's the thing with systems of equations, guys. That's what we got to remember. That's our learning objective. If it makes everything true, if it works for all equations in the system, which in this case was only two of them, but if it works for all those equations, then it's a solution to that system. Let's try another one. Example number 2. Determine whether this point is a solution to our system. This time we have 4, 2. And here's our system. You have 2x minus 5y equals -2. You have 3x plus 4y equals +4. So two equations again. Let's plug them in. X for the x, y for the y. So I'm plugging in a 4 for the x, a 2 in for the y. 2 times 4 is 8. 5 times 2 is 10. 8 minus 10 is -2. True. Okay, so far so good. Let's try it again. 3x and 4y. So that means I have 3 times 4 and 4 times 2. 3 times 4 is 12. 4 times 2 is 8. 12 plus 8 is 20. We needed it to equal 4. We've got false here. As soon as you see that an equation does not match up and that it's false, you know it's not a solution. It needs to be true for every single equation in that system. And there's kind of a shortcut that comes with that. Let's say we tried this equation first and saw that it was false. We don't even have to check the other equation. As soon as you see that one equation does not work, you know it's not going to work for the system. It needs to be true for everything in that system. This one was wrong, so it's not a solution. That's taking points, plugging them in, seeing if there's solutions to the systems. Now, there's a bunch of different types of systems with these systems of equations, and they have different labels and they have different vocab terms. Let's talk about some of those. 3 possible outcomes if you were to graph these systems on a coordinate plane. The two lines intersect somewhere. That intersecting point, that's your one solution, that x comma y. You could have parallel lines, meaning they have the exact same slope, different y-intercepts. They never intersect. They never hit each other. That would be a no solution. You could have something called coincident lines. They're basically the exact same line stacked on each other. Remember, intersecting lines, that one intersection point is the solution. So if the lines are exactly the same, they intersect on every single point. And those lines continue either up or down, left or right, whatever, forever. So every single point on those lines is a solution. That's where you get infinite number of solutions. So you could have one, you could have none, or you could have an infinite amount. Now, when there is at least one solution, that system is called consistent. If there are no solutions, inconsistent system. If the system defines distinct lines, they are independent, meaning those lines are different. They're not the coincident lines. They're different lines, either parallel or intersecting. They're different, independent. If they're the same line, it's called dependent. So we could label these systems based off of those two definitions. We could label it either consistent or inconsistent. We could label it independent or dependent. You're going to see a lot of consistent independent, consistent dependent. You're going to see a lot of inconsistent, and actually, if it's inconsistent dependent, that doesn't work. So you're going to see those three different types: consistent independent, consistent dependent, or just inconsistent. So let's look at an example with that. To do so, without having to graph it, but to do so, we could just change them into our slope-intercept form. And then from that form, we could see what kind of slope we have. And we could tell if it's the same line, if it's parallel line, or if it is different line. So here's example number 3. What kind of solutions does this system have? You have 3x plus y equals 1, 3x plus 2y equals 6. At face value, it looks like we might be the same because we have 3x in both of them. But remember, let's put this in slope-intercept form, and then let's look at the slopes. So I'm trying to get that y all alone. The first one's going to be kind of easy because all I have to do is just take that 3x, move it to the other side, doing the opposite, subtracting. So I have y equals negative 3x plus 1. Next equation, I have my 3x plus 2y. Start the same way. Get that 3x to the other side, subtracting. Now I got to get rid of that 2. It's being multiplied. So let's divide it all by 2. Negative 3 divided by 2 stays as a fraction. 6 divided by 2 becomes positive 3. Okay, so now looking at these equations, y equals negative 3x plus 1. Y equals negative 3 divided by 2x plus 3. Those slopes, clearly different. One's 3 divided by 2. Way different. So since they are different slopes, we know they're going to intersect each other. So we know there's one solution. We could call this thing consistent and independent. Let's do another one. Same type of question. Now we're looking 3x plus y equals 0. 2y equals negative 6x. So again, solving for y. Let's get that y all alone. First equation, same step as before. Get rid of that 3x by subtracting it. It's a 0 over here, so I don't have any constant. I just have y equals negative 3x. Second equation, I have my 2y. It's being multiplied by that 2, so to the opposite, let's divide it. Y equals negative 6 divided by 2, negative 3x. What do you notice about those equations? They are exactly the same. Y equals negative 3x, y equals negative 3x. Since they are exactly the same, this is that type that's called coincident lines. They are identical, which means every single point on those lines are solutions. They go off forever and ever. There are infinitely many solutions. Since there's at least one solution, that's called consistent, but since they are the exact same line, it's called dependent. Last example. How many solutions does the following system have? You have 2x plus y equals 0. You have y equals negative 2x plus 1. Oh, look at that. We already have y all by itself. So let's just move the first one around. I got to get this 2x to the other side, so let's move it to the other side, subtracting just like what we've been doing the last couple examples. The other one's already alone, so now let's compare them. Y equals negative 2x, y equals negative 2x plus 1. Look at those slopes. Negative 2, negative 2. Those slopes are exactly the same, which tells you those are parallel lines. One has a y-intercept at 0. One has a y-intercept at plus 1. So they have the exact same slope, but they're not the same line. Guys, these things are never going to intersect. They are never going to hit each other. Because of that, there are no solutions. There is not any combination of X and Y that you could plug in to make this thing true. If I was really mean, I would have you plugging in a bunch of different solutions trying to see if it's true or not, because I know there are no solutions. So you'd be checking a list of numbers all day long trying to find one. You never would. Luckily for you, I'm not mean. I'm just telling you right now there's no solution. But we were able to figure it out because we put it in slope-intercept form. We noticed slopes were the same, but the lines were not exactly the same. Parallel lines, no solutions. Now, if you do not have any solutions, that's called inconsistent. The lines are still different. They're still distinct lines. So they're independent lines. But because you have no solutions, you're inconsistent. So there's a quick look at plug-in values in, seeing if it's a solution to the system or not. There's a quick look at the three types of systems we have: the consistent independent, the consistent dependent, the inconsistent independent. Looking at whether it's one solution, infinitely many, or no solutions. There's also one last thing I wanted to do with this Edpuzzle video today, guys. What I wanted to do was talk up the delta math that we started on Monday, because we might need a little, like one more example just to see it all through. So looking at this one here, remember they were talking about apples, bananas, nickels, dimes, quarters. They were talking about a bunch of different stuff. You just had to match it with what they were asking for. This very first thing for me says, determine 3 ways to have 4 times as many nickels as dimes. I want 4 times as many nickels. So let's say I have 1, 2, 3, 4, and 1. Now I can plug it into my parentheses. I have 4 nickels, 1 dime. 4 times as many. I could probably try 0, 0, but I think it's going to be a little tricky. So I'm going to go to the next one. I'm going to say I have 8, because I know 8 divided by 2 is 4. I know 8 is 4 times 2. So I got 8, 2. Now they wanted 3 ways. I found 1. I found 2. I got to find 1 more. Following the same logic. 1, 2, 3. 3 times 4 gives me 12. 10, 11, 12. So let's put that in our parentheses. 12, 3. Guys, do you realize what they're doing with this stuff here? All of these nickels, dimes, all this stuff we're putting in our parentheses, those are the x, y's. Those are the values that might be possible solutions to our systems. Now they want us to graph it. Pick any of these points. I have 8, 2. I have 12, 3. So I'm going to go to 8, 2. Then I go to 12, 3. There's my first line. Do it again. Be very careful, though. This time they don't want 4 times as much. They want a total of 90 cents. So one quick way to make 90 is just to have 9 dimes. That was 0 nickels, 9 dimes. I could do it all in nickels as well. Let's say we have 18 total nickels. So I could do 18. Oops. I need 1 more of those nickels. I could do 18 and then 0 dimes. Then the third way, I could do a mixture of both. Let's say I had 50 cents from nickels, 40 cents from the dimes. That's 90 altogether. So I could say, what was that? 10 nickels, 4 dimes. Adding up to make 90 cents, however you can do it. Then plot the points again. You have 10, 4, 18, 0. So I had 10, 4, 18, 0. Think about our consistent independent. Think about our consistent dependent. Think about our inconsistent. Take a look at these lines that you graphed. They intersect at 1 point. With that 1 point, that's a consistent independent. That's our solution. We had 12, 3. So I have 12 nickels, 3 dimes. Piece of cake. Email me if you have any questions, guys. We'll talk to you all later.